All right. Good morning. Actually, good afternoon at this point. Feels like morning. So, hello. Thank you for coming. I'm Bodil, and I'm going to teach you functional programming today. Or rather, do you all know what a hipster is? A hipster is, how to put this kindly, someone who perhaps likes to feel a bit superior to everybody else and likes to show that he is a bit better than you. And of course, in our field, programming, hipsters tend to go, for some reason, for functional programming. And so the concept of my talk is that I would like to help you feel superior to everybody else through just teaching you to use the language of functional programming. So I'm not going to show you how to apply this to your actual everyday work or anything that actually makes sense or helps you at all, except for the bit where you can actually just relax and feel smarter than your colleagues. There are four great paradigms in programming that have developed over the years. There's the procedural programming, exemplified by languages such as C, and that's one of the guys who invented C right there. They tend to live on very far back on the back end in the operating system and stuff like that, and in games and things that require absolute speed. So there's the object-oriented programmer, of course. Picture here in the usual habitat. I'm sure you've seen this. I know I have. It was pointed out to me yesterday that object-oriented as a paradigm is more orthogonal to the rest of them. But especially in the Java world, it tends to be overpowering in its presence in the language. I mean, Java is you could think of Java as a procedural language, but the object orientation takes so much precedence. There's also the functional programmer. And they tend to come from academia quite frequently, use strange language that most of us don't really either care about or need. And yeah, they do get a bit stuck up at times over this. But that's a great bit about being a functional programmer. And finally, of course, there's the logic programmer. And, well, humanity isn't quite ready for logic programming yet, I'm afraid. So we're going to leave it at that. But someday in the future, perhaps. So, in summary, you don't really have to worry about these four great paradigms, because there are only two that really matter. There's a functional programmer, superior to you, smarter, likes to show off about it. And of course, there's the object-oriented programmer, or the muggle, as we like to call them. So, yeah. And much of what is really confusing about functional programming comes from a wonderful language called Haskell. It is a pure functional language. It offers referential transparency. It offers a lot of things that only an academic could really appreciate, I suspect. But in particular, it borrows a huge vocabulary from a field of mathematics called category theory. And this is a treasure trove of confusion. There is so much in category theory that just makes the average programmer's head kind of blow up a bit. And you might find that the concepts that category theory expresses are concepts that you have been using in your everyday programming life, just that they have a much more intimidating word for it. And I'm going to try and teach you some of these words today. So, I'm going to start at the start and show you the basics, the very essence of what functional programming means. And I'm going to tell you a story. Oh, sorry, is that still there? So cats are like totally lost year, so I'm going to try something new today. Cats are too mainstream, sorry. So, yeah. Well, story time. Once upon a time, there was a man called Haskell. He's the guy, the language Haskell, of course, is named after. Haskell Curry invented something called the lambda calculus. The lambda calculus consists only of functions. And it is, of course, a pure mathematical exercise, really. You wouldn't actually find any use for this outside of mathematics. But if you like mathematics, you should totally learn that. So that was lambda calculus, part one. There was also a guy called Alonzo Church, who he was one of the first type system geeks. So he saw Curry's lambda calculus and thought, this is cool, but it needs more types. So he added types to the lambda calculus, and that introduces the type lambda calculus. Now, this is all just mathematics. Until a guy called John McCarthy, as an exercise, took the lambda calculus and created a syntax for it, in essence, which was still just mathematics. It was just, let's say, a better way of working with the lambda calculus. But one of my students, just as an experiment, took that and wrote a compiler for it, or an interpreter for it. This was back in 1958, so I'm not going to venture a guess at what kind of computer that was, but it was probably huge and slow. So it turned out this was actually a very nice programming language. That was called Lisp. That was in 58, and it's been with us ever since. That was the first functional programming language. Now, let's just dive right in. Functional programming is characterized by the idea of first-class functions. That functions are values that can be passed around, just like, say, strings and numbers in your average non-functional language. So, let me show you how that works. So I'm going to be using JavaScript today. Is that okay with you? I figured just everybody can at least read JavaScript, at least a little bit. I'm not going to be using any complex JavaScript, except for one thing. This isn't actually JavaScript. This is TypeScript, Microsoft's version of JavaScript with type checking. So you see, I put a string behind the function. This means that this function is supposed to return a string, which means that, let's try compiling it. That seems to work. If I were to change, wow, what happened? This is not good. Hello? I think I'm actually struggling with connectivity at this point. I'm connected to something. What is that? IBAN. That is not right. I'm not supposed to be connected to anything. I'm just going to turn my Wi-Fi off. Technical problems, yay. Okay. There we are. Let's see if that works. That works a lot better. Now, I'm supposed to be able to delete that string. Thank you. Thank God. So if I compile that, it's going to say that, hey, you're trying to return a string. It's supposed to be a number. This is an error. So that's TypeScript, in essence. This function takes no arguments, so I'm not going to show you how to type annotate arguments, but you get that as we go. No worries. So let's call that function. It returns the string hello everypony. So this is hello world in functional programming. Of course, if I just try and get the value of hello instead of actually calling it, it returns a function. This is a function as a value. This is a first-class function. It means a few other things. For instance, I could perhaps okay, something more descriptive. Oh, hi. I can take the value of hello and assign it to another variable, oh, hi. And of course, I could just call that, and that works. That's the same function. So you see that the functions are values that we can reassign, but more importantly, we can pass them along to other functions, and that's where it gets interesting. So moving on, functors. Now we are approaching some of the vocabulary that us functional programming hipsters so like to use to confuse you muggles. A functor. Well, in some languages, functor simply means function. I believe Prolog is an example of that, but Prolog is logic programming, and I promise you I wouldn't do that. So a functor, at least in the Haskell sense, is a collection of x that can apply a function f that takes an x and returns a y over itself to create a collection of y. That's clear, right? Any questions? No, thank you. No, actually, what this means is that most languages have a list data type of some kind, a sequence, an array, what have you. And the functor, this is common in the vocabulary of category theory. A functor is not the list. It is not the function, the map function that applies your function to the list. It is both. It is both of these things, the list and a map function. The map function simply takes the list and it takes your function, f x to y, and it applies that to the list, creating a new list where each element of the function has been run through, each element of the list, sorry, has been run through that function, and the new list contains the return values of that. So let me just show you, because this is so much easier to understand with an example. Suppose we have a function caps. It takes a string, it returns a string. Oh, bonus points. A functor where the function you apply returns a value of the same type is an ender functor. Ender functor. That's a great word for confusing people. Sounds very impressive. So, we have a function caps which takes a string and turns it to uppercase. We have a function map, which is part of the functor. I'm going to implement that for you. And we have a list of ponies, because you got to have ponies, right? So, this is how you implement the map function. We're going to create a new list, so we just create a variable for that. We want to iterate, so we create an iterator variable. And we do a simple for loop. Everybody should know the syntax for this for loop, right? It's from way back in C times. So we simply loop, incrementing I until it's reached the length of the list. So we're just iterating over the list in essence. We take the new list and we add the result of calling func. Notice func is a parameter, which is a function, which takes one argument and returns one argument of any type. And the other argument is, of course, the list. So we take func and we call that with list I. That is the current element of the iteration. And we take the result of that and push it onto the new list, which should apply the function over each element, and we just return that. So, that's easy, right? It compiles. Let's try running it. Map caps over ponies. See that? That returns the list in all caps. So the map takes, the caps function takes just one string and it outputs another string. And we just applied that, we mapped that function over the list of ponies. And that, ladies and gentlemen, is a functor. It's no harder than that. Of course, there's another function that usually goes with map. It's called filter. Filter is similar to map, but the idea is that instead of transforming the list, we're going to filter it by sending filter a function that returns either true or false. And if it returns false, the value doesn't get to be in the new list. Otherwise, it's just copied over. So just the same iteration as before. except this time we're going to do an if. And if func of list I returns true is implicit in JavaScript, but I could also go like this, if you like, but I'm not going to. So if that returns true, then we push the value onto new list. Otherwise, we don't, quite simply. And of course, we have a function here called toCool, which tests if a pony is too cool to be in the list. And Rainbow Dash, obviously, is way too cool to be in any other list. So let's see if we still have the ponies list. We should. We do. So let's try applying the filter. We filter too cool over ponies. That should give us what? The list will Rainbow Dash removed. And Rainbow Dash is removed. Now suppose in an upside down world, Rainbow Dash is the only pony that isn't cool, isn't too cool. I mean, the idea is absurd, but just pretend. So that returns a list with just Rainbow Dash, because that was the only one that returned true. Enough of this heresy. Rainbow Dash is too cool. Right, and that's the filter. Moving on. Reduction. Actually, what we've been doing with both map and filter are special cases of a thing called reduction. You probably heard about map reduce, right? That's the map and a reduction, which is kind of confusing. But anyway, so the idea of reduce is that we have a function that takes two arguments. And we have a list, as usual. And the idea is that we start with an initial value. And the initial value, let's say that becomes the A in this function. And the B is each value of the list in turn. And we kind of squish them together. And the most obvious case for applying a reduction is to create the sum of a list of numbers. So let's just create a list of numbers. Why don't we? Oh wait, we didn't have to create a list. I'm going to implement the reduction. So result, that's where we are going to keep track of the results of the reduction. It's going to start out with being just initial, which is the input value. And we need an I. And we're going to do the for loop again. List.length, I++. But this time, we are going to just kind of increment result. So func of results and initial. Sorry. Initial is, of course, result at this point. So the result of calling the function with the current result and the value we're looking at in the list is accumulated here, and we just return it at the end. Result. Right? Oh, I forgot to mention, if you see me making a typo, I'm not actually testing you. You should tell me, okay? Which means that if I make a mistake programming up here, that is your fault, right? Great. I'm glad we understand each other. So, let us try applying that reduction. We reduce with add over list of 1, 2, 3, 4, 5. How about that? What's going to happen now? Whoops. What did I do wrong? I forgot to supply the initial value. That should be 0 for a simple addition. 15. That's the sum of 1, 2, 3, 4, and 5. So that was quite easy. Moving on, here's the reduce function again. And, oh wait, I lost my point. Sorry, here's the reduce function. So the thing is that I mentioned that map was a special case of a reduction. So I'm going to show you how to do a map with just the reduce function. Which means I have to create a function that is that actually does the mapping for us. Let's call it shouty map reducer. It takes a list of strings and just a string, and it returns a list of strings. So what we do here simply is we concatenate a list that only contains 2 uppercase of B onto A, which means that the initial value shouty map reducer, I should have come up with a shorter name for that, with ponies. I hope we have ponies still. We should always have ponies. Let me check. They are still there. So, with an initial value of an empty list, was my point. So the idea is that A is going to be an empty list at first, to which we concatenate the list that contains only 2 uppercase of B, which is going to be the first pony. And then A is going to contain the first pony uppercase, and the second pony is going to be uppercase and concatenated, and so on. Which means that the list of ponies, just for reference, the list of ponies, rainbow dash, pinkie pie, twilight sparkle, becomes the list of capitalized ponies. So that was me doing a map with a reduce. So we see that map is just a special case of a reduction. You can filter it the same way if you like, but I'm not going to. I think you got that. So, higher order functions. Actually, we've been kind of doing that already, because a higher order function is defined as a function that takes a function as input and or returns a function. And what I'm going to show you now is a function that creates functions, which is starting to get complicated, right? So, here's caps again, because there's nothing better than shouting a bit every now and then. So actually I'm going to show you how to generalize shouting map reducer, because you don't really have to do the mechanism of the map each time. So instead of shouting map reducer, I'm going to create a generic function, map reducer, which takes a function in, which takes 1 argument and returns 1 argument of any type. And this returns a function. Now it's getting interesting. Make sure you pay attention now, there's going to be a test. This returns a function A, which takes arguments A and B, which you will recognize is a function that goes into the reduction. So, this simply concatenates the application of func onto B, onto A. So what this does is it generalizes shouty map reducer. Let's try reducing shouty map reducer over ponies and empty list. See, that works as it used to do. Now, you'll notice we have caps at the top still. How about we use our map reducer higher order function? Map reducer of caps. That's going to return a function that essentially does the same as shouty map reducer, because caps is the func in this case. So let's see if that works. It produces the same result. In case that wasn't obvious, I'm going to remove it and run it again. See, that was a higher order function that helps you create a function that can be used to map, which is just reduce. Okay, combinators. Disclaimer. I'm taking liberties with the term combinators at this point. If you're a mathematician, please don't be offended. My definition of combinators for this purpose is a function that just wraps around a function and produces a function that returns, that works in a slightly different way. It takes no input except that function. And it works in a fixed way. That's the core of it. There's this whole field of mathematics called combinatorial logic that I'm definitely not going to go into. But you get a lot of nice and confusing combinators out of that, trust me. The Y combinator, everybody's heard of the Y combinator, right? That's a combinator that lets you essentially introduce recursion into a language that doesn't support it. There's the S combinator, there's the B combinator. All the combinators are named after letters for some reason. But that's cool. So, we have a function square. Can you imagine what that function does? Square root of 5, what's that going to be? Yes, 25. Now, let me show you the world's most useless combinator. And 3. The and 3 combinator. It takes a function, as you'd expect. I'm not going to bother with the types there, because you get the idea. And it returns a new function, which has the same signature as square. And, oh, no, sorry. Confusing myself. So, it simply takes the result of calling that function and adds 3, which means that square root of 5 is 25, and 3 of square called with 5 as an argument is 28. We could go like, just make it explicit. Square and 3 is the and 3 combinator applied to square. So we can go square root 3 of 5 is still 28. So that was a combinator. That was a stupid combinator, though. You want to say combinator that actually does something useful. So suppose we have an object, Pinky, and a function pony type, which takes a pony. A pony is an object that has a name and a type. And it returns the type of that pony, which means that we can call pony type of Pinky, and that should tell us Pinkie Pie is a Pegasus pony. Now, at this point, I'm wondering if somebody would like to object. Because this is where I found out if there's actually a brony in the audience. Because obviously, you guys are so stupid. Pinkie Pie is an earth pony. See, now it works. But suppose we have another pony called Rainbow Dash. And for some reason, Rainbow Dash couldn't be fetched from the database or whatever, because she's way too cool for that shit. So, suppose we call pony type with dash. That gets us a type error. That's actually an exception, and that's going to break your program. So I'm going to introduce to you the null check combinator. I feel like I'm mangling the terminology, but never mind. It takes a function that takes one argument, and it returns one argument, as usual. And it returns a function that takes the same argument. And if that argument is null, then we just return null. Otherwise, we return the application of func onto that argument. Now, what's going to happen when we call pony type on dash? Same thing, because we haven't applied the combinator. If we apply the combinator onto pony type and call the resulting function with rainbow dash, who is still null, we're just going to get null. So that was a cheap null check. I mean, you would probably want to handle this error in a different way in reality. But that was an example of a combinator at least doing something useful. So, moving on. Composition. This is where I start to feel like we're actually talking about real functional programming. Composition is the idea that you can take two or more functions and kind of squish them together to make a new function which does what all of those functions do in sequence. So we have caps again, and we have high. Caps of every pony returns, of course, every pony caps. High every pony returns hello every pony. Now, let's create a compose function. We're going to create a simple compose function that only takes two functions. So func1 takes one argument, returns 1. Func2. You might be wondering why I actually bother with TypeScript, because all I'm doing is saying, specifying how many arguments the function takes. I don't usually bother with types. TypeScript's type system kind of sucks a bit. So there you go. So at least we know that we take two functions. Each function takes one argument, returns another. Very generic compose function. No, very specific, sorry. So we return a function that takes one argument and calls function 2 on function 1 of that argument, which means that function 1 is first called on the argument, then function 2 gets called on the result of calling function 1 on that argument, and the result of that is returned. So we kind of chain functions together, in essence, to operate on a value, which means that we can compose caps and high and call that with every pony. Now what's going to happen? Let's just check. Every pony gets capitalized. Caps get called first on every pony. Then high gets called and adds hello. Suppose we change the order of that. High, then caps. Then hello gets capitalized too. So the order matters. Actually, that's composition for you. It's the idea of taking more than one function and chaining those functions together to make kind of a processing chain. You start with an input value and you can add steps to how you want to process it. This is starting to sound a bit like how you'd work with big data. Moving on, applicative functors. This is my favorite. Applicative functors. That's a huge and lovely confusing word. And there's a good reason for using a confusing word for it. Because when you see my application for it, you can see that it's kind of complicated. Now an applicative functor, that's like a functor, except it also has an applicative map function. And what the applicative map function is, obviously I'm not going to type this out on stage. I already wrote it for you. The implementation isn't important. It's JavaScript, so it gets complex because JavaScript is kind of stupid. Now, applicative map, that takes any number of lists, any number of functions, and kind of applies everything to everything. And I'm just going to have to use an example to hope to explain that. Suppose that we have an applicative map of high and caps, and we have the ponies. Notice, instead of the function that I want to map, I pass a list of functions, which means that each list, in turn, each function in the list, in turn, is applied to ponies. So we get hello Rainbow Dash, hello Pinkie Pie, hello Twilight Sparkle, and then we get the caps of those. So AMAP tries very hard to apply everything to everything, every function to every member of the ponies. Now, you can go on. It can work on more than one list. And what that implies is that the functions get called with multiple arguments. So if you have two lists, you need a function that takes two arguments. Suppose we create one. Function hug. And hug takes pony 1 and pony 2. Of course, ponies like to hug. So P1 hugs P2. Isn't that adorable? Right, so let's try and pass hug. But we need more ponies. Other ponies. You want to help me out? You want to do the whole of the main 6? So we have Rainbow Dash, we have Pinkie Pie, we have Twilight Sparkle. Huh? What's that? It's not in the main 6. Right. If you didn't catch the Earth Pony thing, then yeah, I'm going to help you out. So there's Rarity. There's Apple. Jack. And Fluttershy. You guys. Okay, so now we use the application map to apply a hug to both ponies and other ponies, which means that Monads hugs rarity, and then all the others in other ponies. Notice that every member in ponies hugs every member in other ponies, and that's very important. Now, that was applicative functors. You might be wondering at this point, what's the use of applicative functors? It's complicated. You might figure it out. I'm not going to show you. I've shown you how to do an applicative functor, which means that you can use the word applicative functor. Like in your everyday work setting, you can just walk over to a colleague and say, I think you should be using an applicative functor there. And you know you're superior to them. Yeah. Anyway, applicative functors are actually very useful in languages like Haskell and Scala. You should check them out properly. So, currying. You notice I'm using the world's most overused image to represent currying at this point. I'm of course doing that ironically. A bowl of curry, yeah. So currying. Can you imagine where the term comes from? Which person that term comes from? Haskell curry, obviously. Not actually the food. So currying is the act of transforming a function of several arguments into a chain of functions of one argument that will yield the same result when calling a sequence with the same arguments. Right. Actually, it's easier if you look at the function. A function that takes 3 arguments can be curried into a function that takes 1 argument, that returns a function that takes the 2nd argument, that returns a function that takes the 3rd argument, and returns the result of f with those 3 arguments. So, as I mentioned, it's named for Haskell Curry, but he didn't actually get there first. And this is a bonus point, ladies and gentlemen. If a colleague of yours catches you trying to impress them by using the word currying, you can up the game. Because actually there was this guy called Moses Schoenfinkel who actually discovered the principle of currying a couple of years before Haskell did. So when somebody uses the word currying back at you, you can just go, I think you mean Schoenfinkeling. Yeah. So, currying. I've implemented the curry function here, because it's kind of messy having to do this in JavaScript. Actually, JavaScript kind of comes with the currying built in, but I wanted to make it explicit for you. So, here's the currying. Here's a concept I'd like to introduce, because this is a word that most people don't know. Arity is not a pony. It's... What arity means, quite simply, is the number of arguments a function takes. So a function that takes 2 arguments has an arity of 2, which is going to be useful in a curry function, because in JavaScript we can't reflect on the function to discover how many arguments it takes, so we have to be explicit about that. I created an add function that takes any number of arguments. This is how you denote that in TypeScript, which means we can go add 1, 2, 3, which results in 6, right? Now let's curry that. Curry add 3. That returns a function. Let's call that function with 1. That returns a function. Let's call that function with 2. That returns a function. Let's call that function with 3. What's that going to do? 6. Which means, by the way, one and 2 and 3. Oops, did I have a typo? Yes, I did. It's 6. Yeah? So currying, what I've actually shown you here is the most common application of currying, which is called partial application. Mind you, most people, when you talk about currying, just assume that you mean partial application. This is wrong. Currying has several uses. Partial application is by far the most common, but currying does not mean partial application. So whenever you catch somebody use the word currying about what is actually a partial application, you can shut them down on that. Partial application, incidentally. So this is a more useful version of just the special case of partial application. We still have the add function, we have a partial function up here, and we can go partial with add, and then pre-fill some arguments. Let's just stick with tradition and go 1 and 2, right? So 1 and 2 and 3 is 6. We could go like add a 6 to that, and suddenly it's 12. So the idea is that partial application takes a function with a number of arguments and pre-fills the first arguments, as many as you specify, and returns a function with those arguments pre-filled. So you can just call it with the rest of the arguments, and you're going to get the result of the curried arguments and the actual arguments. So that's partial application. I was going to try and explain it a bit more for you, but I see I'm running out of time, so I'm just going to rush on because the most important bit is still left. Monads. Monads, I love them. Nobody understands them. And the beauty, in fact, of monads is that, actually, I think there's a conspiracy. Because there are so many monad tutorials, and all they do is confuse you even more about what monads are. Once you get it, though, it's so simple that you start to realize that all those monad tutorials were probably written by people who understand monads and don't want you to understand them as well. Which is, I mean, that's typical of functional programming hipsters for you. Anyway, monads were, of course, invented by Philip Wadler, the only academic I didn't actually need to Photoshop for this presentation. Actually, monads weren't invented by Philip Wadler, but until Philip, nobody thought to use monads in programming. They were strictly for the mathematical side of category theory. But Phil was one of the inventors of Haskell, the language. And what he contributed, because Haskell, as I mentioned, is supposed to be pure and have no side effects. And how do you write a useful program that has no side effects, not even I/O? That's just stupid, right? Of course, academics appreciate the purity of such a language. So they had to go and create one anyway. And Philip actually made it useful because he discovered that with monads you can actually cheat and have side effects using monads. And so you get the idea that monads are kind of magical, and they are. But in category theory, they're explained by the 3 monad laws. And these are not the 3 monad laws. The first monad law is you do not talk about monads. The second monad law is you do not, yeah, you get the idea. Actually, there are 3 laws about monads that make sense, and they probably make sense to mathematicians. You don't need them to understand monads. And another wonderful thing about monads, the most wonderful thing, is that there's a synonym for monad, and it's Kleisli triple. How about that? I love that word, Kleisli triple. It maximizes the confusion of the people you're talking to in just a beautiful way. So remember, start talking about monads, start talking about Kleisli triples, so the muggles can't follow you. So I'm going to show you a use case for monads in the short time that I have left. So this is going to be my input data. This is just HTML. This is an HTML list, an ordered list, which contains list items with ponies in them, and sub-list items with each pony's corresponding element of harmony. If you don't know what an element of harmony is, you need to watch My Little Pony. You need to watch My Little Pony anyway, but you get the idea. So what I'm going to do is I'm going to take that list of ponies and get the elements of harmony as a list. which means that I need a function called children, which takes a DOM element and returns a list of that DOM element's children. As you see, input is one element, output is a list of elements. That's important. Now, I get the ponies list, put it in the variable ponies, and call children on that, and I get the ponies, obviously. Now you remember composition. So obviously, what I want to do when I want when I want to get the grandchildren of the ponies list, I can just compose children, and it's going to get the grandchildren, right? No. Because the problem, of course, is that what comes out of the first call to children is a list of elements. And the second call to children expects just one element. Fortunately, there's a monad for that. There's a monad for everything. But in this case, I'm just going to show you one of the absolute simplest monads, called the sequence monad, or the list monad sometimes, or the array monad. The idea is that there is a list of some kind, and the sequence monad is used to adapt functions for composition. Well, I'm just going to show you. What I need is one part of the monad called the unit function, which takes a value, which can be anything, and returns a list of values. And that list of values is simply a list with that value, which means I take the input argument for children, essentially, and creates something that is suitable for composition. And the other part of the monad is bind. So I'm going to totally skip the types now because I'm running out of time. Bind takes a function. It only takes a function. And yeah, skip the types. And it returns a function that takes a list. And quite simply, it does something a bit like the map. Out for I equals 0, I is less than list length, I plus plus. And we concatenate each call of function onto out. And then finally, we return out. What this function does is it kind of takes children, which takes one element and returns a list of elements, and adapts it to take a list of elements and return a list of calling function on each of those elements. Which means that now we can bind children into the sequence monad, and that should do the trick, right? Whoops, we still need to apply unit. So, because the bound children now takes a list of elements, we have to use unit to convert our ponies argument into a list of ponies. Now, we're not quite there yet, because now we just got the inner list, and we need the list items. But we can just keep doing this forever until we run out of arguments. But this produces the elements of harmony. And that was the sequence monad. The sequence monad, in essence, is just an adapter for a function that isn't composable, which means that it does not return the same type as what it takes in. So, monads. Whew, I made it. Monads. Whew, I made it. 1 minute. I'm going to rush through the last. Because there is, of course, more. Haskell is an endless source of confusion. And this is my favorite part. Zygohistomorphic prepomorphisms. I kid you not. That is actually something that is in Haskell. It's speculated that it was put there as a joke, but it does actually have its uses. I mean, it's obvious when you think about it. A zygohistomorphic prepomorphism is a prepomorphism that also has zygomorphic and histomorphic properties. Yeah? By the way, the text you see underneath there is the only documentation that Haskell provides for zygohistomorphic prepomorphisms. I love Haskell. You just have to learn it. It's going to blow your mind, and it's going to... It's going to provide so much confusion to your coworkers. We're done, in fact. Fortunately. Yeah, one more thing. If even Haskell doesn't do it for you, logic programming is there for you. So thank you very much. That was me. Slides are there. If you have questions, find me later, because we're totally out of time. Thank you.